Thanks for your patience. Let's see, I'm waiting for my images to show up before I start to talk. Hopefully my image will show up before I start to talk. There we are. Okay, good. What I'm here for is to give you a sort of an introduction. We're going to have a discussion about open questions in cosmology in a few minutes. But I'm going to give you an overview of our current picture of the universe. And I figured since we're in New York, I should begin by telling you these are stars. And you may not have seen them before. They're at night, they're up there. But if you go in the country, you might see this kind of picture. This is a globular cluster. And the stars are absolutely beautiful. But what we have learned in the last 25 years is that as beautiful as they are, they're really just the tip of a vast cosmic iceberg. And the really important stuff is the stuff between the stars. And we are just beginning to learn about that stuff. And there are huge mysteries that are related to it. And I want to set the stage by explaining to you what we know and most importantly, what we don't know about the universe. So I always begin with this guy who gives me great faith in humanity. This is Edwin Hubble. He began life as a lawyer and then became an astronomer. So there's really his hope for everybody. And he changed our picture of the universe tremendously. And we're going to be talking about history a little bit, so I just want to point out, to put in perspective, his greatest discovery, which I'll talk about in a minute, has to do with the dynamics of the universe. But about a little over 80 years ago, when the first large telescope, Mount Wilson, was built, he resolved a big problem. When people looked out in our galaxy, and by the way, at that time, 80 some odd years ago, there was one galaxy in the universe. That was it, our Milky Way galaxy. And when you looked with telescopes, you saw some fuzzy things that were called nebulae, which is Greek for fuzzy thing. And there was a big debate about what they were. And with that telescope, he was able to resolve the fact that, in fact, these nebulae, many of them, were in fact other island universes, other galaxies. We now know that there are 400 billion galaxies in the observable universe. And 80 years ago, we knew of one. So we're like the early map makers. In fact, one of the map makers is here, and we're going to talk on stage about this stuff. And it's therefore not surprising that our picture of the universe is dramatically changing all the time. It's a very exciting time in cosmology. But the discovery that he made that made him famous, of course, was that the universe was not static and eternal. Up to that point, scientists, that was the conventional wisdom in science, that the universe had been around as it was, more or less, forever. And he convinced the world that it wasn't by an observation which he made. These are not sperm, these are galaxies. And what he discovered was that as he looked out from our galaxy here at other galaxies, they're all on average moving away from us. And those that are twice as far away from us are moving twice as fast. Those that are 3 times as far away from us are moving 3 times as fast, etc. Everything is moving away from us. And this obviously tells you that we are the center of the universe. Okay? Now, that's what it naively would suggest when you look at it, but it doesn't imply that. It implies the fact that the universe is expanding uniformly. And there are lots of different ways I've tried to demonstrate this to people, but I think the only way to really see that this implies the universe is expanding is to get out of our myopic position where we are. In fact, really the best way is to get outside of our universe and look in. And so what I've done here is to draw a 2-dimensional universe where we're outside of it easily enough, and we're looking at a universe. Now I put each of the galaxies at a nice uniform distance apart at some time t1, and now if the universe is expanding, all those galaxies are a little bit further apart at some later time. So if you were standing outside the universe, it'd be obvious that the universe was expanding. But what would you see if you were in that universe? Well, pick a galaxy, any galaxy, that one there. And to understand what it would look like from that galaxy, I'm just going to superimpose this image on top of this one, placing this on top of where it was before. And what do you see? You see exactly what Hubble saw. Every galaxy is moving away from that one, and those that are twice as far away has moved twice the distance at the same time. Those that are 3 times as far away, 3 times, etc. And the point is, it doesn't matter where you are. Any place you are, you see exactly the same thing. Everything is moving away from you. So if you're a pessimist, there is no center of the universe. An optimist, every place is the center of the universe. But what it really means is that what Hubble saw tells us that the universe is expanding. And that is profoundly important because it changes cosmology And it's really one of the reasons we're here, because if the universe is expanding, yesterday it was a little smaller than it is today, and the day before a little smaller. And if we work backwards, at one point, a time that we now know about 13.7 billion years ago, all of the observable galaxies in the universe and all of the matter associated with those galaxies was contained in a region smaller than the size of a baseball. And that means to understand that universe, we don't just think about astronomy, but in fact about the physics of the very small. And what really this is a famous alchemy symbol called the Ouroboros, which is a snake eating its own tail. And that really sort of represents cosmology, because at the very biggest scales, to understand the universe at the very biggest scales, we really have to think about physics at the very smallest scales. Because at the earliest moments of the Big Bang, it was the physics of the very smallest scales that determined what would happen. And those are some of the things we're going to be talking about in the panel later. Now, this is Hubble's data. I'm not supposed to show graphs here, but I lied. I'm doing it. It's important to see this because it gives you a sense of how cosmology has changed, and also one of the reasons why he was such a great scientist, in fact, because he knew to draw a straight line through this data set. But this is velocity versus distance. And he saw that objects that are further away from us are moving faster, he interpreted this to be. Now, he did something very important. He got the answer wrong by about a factor of 10. And that's a tradition we've tried to continue in astrophysics. And, but it is, the reason he did it was not that he wasn't a good observer, but it's very difficult to determine how fast the universe is expanding. In fact, it's taken us 80 years to really get this down pat because, well, it's easy to measure velocity. It's hard to measure distance. Velocity is easy to measure, and in fact, these two cowboys know how to do it. They're on the plane, and one of them is turning to the other and says, "I love hearing that lonesome wail of the train whistle as the magnitude of the frequency of the wave changes due to the Doppler effect." And so we see galaxies and moving away from us, and we know they're moving away from us because we see the light from those galaxies stretched out by the Doppler effect. And the long wavelength end of the radiation is the red end of the spectrum. So when objects are moving away from us, we say they're redshifted. And what we found is that objects that are farther away are redshifted more than objects that are closer. But the big question is, how do we know they're farther away? That's the hard part. How do you measure distance? Velocity is easy. Distance isn't so easy. In order to measure distance, you have to, what we've tried to find is something called a standard candle. An object whose intrinsic brightness we believe we understand, like a 100-watt light bulb. I could measure the distance to the back of the room if I turned off all the lights except for a 100-watt light bulb, and if I had an old-fashioned camera, older than many of the people in this audience. They used to have a light meter. If I saw how much power was coming into my camera, and I knew it was a 100-watt light bulb back there, I could work out how far away the light bulb was. So if the universe were populated by 100-watt light bulbs, we'd be fine. But it's not. And we have to look for the equivalent, something whose brightness we understand. We look through a telescope and see how bright it appears. If we know its intrinsic brightness, we can figure out how far away it is. And that's the hard part of measuring distance. And that's been very hard for 80 years. And in fact, what we now have is a great standard candle. And the first image I showed you was this picture, one of my favorite pictures. This is a galaxy far, far away and long, long ago. And this is a bright star. And now this star is as bright as the center of this whole galaxy. And you would therefore think that what it is just a star in our galaxy that got in the way of the picture. But it isn't. It's a star on the edge of this galaxy, and it is shining with the brightness of 10 billion stars. What happened? Well, it's a star that's just exploded. It's a supernova. And supernovae don't explode very often, fortunately for us. They explode about once per 100 years per galaxy. But they do explode, which is important for all of you, because every atom in your body almost was once inside an exploding star, because that's where all the heavy elements on Earth were made, in exploding stars. So you really are star children. But they don't explode very often, and therefore you might say, how can we use these things? And the other thing I want to point out is that the amazing thing about the universe is that it's big and it's old. And therefore rare things happen all the time. And if you hold your hand out at arm's length and held out about a dime-sized hole and looked at a dark spot in the sky, if you had a telescope that was powerful enough, you could see about 100,000 galaxies. And if you work it out once per 100 years per galaxy, 100,000 galaxies, on a given night you would see 10 stars explode, you would expect. And astronomers do that. They actually apply for telescope time and say, tonight I'm going to see 10 stars explode, and they might see 9, They might say 11, it might be cloudy or whatever. And we can use these objects. In fact, these are new standard candles, and we can actually see them explode in real time. Here's a little movie of a star exploding in a distant galaxy. They remain bright for about a month or so. We can measure their brightness, and from their colors, we can tell what kind of exploding star they are. And a certain type of supernova has become a wonderful standard candle that has allowed us to measure the expansion of the universe. And here's a new Hubble plot. You can see how much better we do. This is, of course, also after the important mathematical discovery that on a log-log plot, everything is a straight line. But in any case, we now can measure the Hubble constant to about 10%, as opposed to about a factor of 10. And that may not sound like much, but it's really been important. And it's been important because it turns out, if we want to determine the future of the universe, we have to understand the expansion rate. Because, as Einstein told us, with his general theory of relativity, which governs the dynamics of an expanding universe, we think, and we'll talk about to what extent it may or may not ultimately govern those dynamics. But if it does, then the neat thing about general relativity is it tells us that matter curves space. Energy, radiation, matter can curve space and cause it to dynamically respond by expanding, contracting, etc. And that means we live in one of three types of universes, a so-called open, closed, or flat universe. The geometry of those universes are different. And now, of course, these are two-dimensional images. It's a lot easier to draw a two-dimensional curved universe than a three-dimensional one, which is why I have it here. But what really got us interested and why we wanted to know, and why I, in fact, became a cosmologist from originally doing particle physics, is it turns out that, that what's really important about these universes is in a closed universe, if it's full of matter alone, it will expand up to a certain point and then contract into a reverse of the Big Bang, a big crunch, if you want. So a closed universe would expand and then contract. An open universe would expand forever at a finite rate, and a flat universe was just the boundary between those two, which would almost stop but never quite stop. And the real question in cosmology over the 20th century was, what universe do we live in? That's what we wanted to know. And in order to know that, there's two things we have to know: how fast the universe is expanding, measuring the Hubble constant, and how much matter there is, because we wanted to know whether there was enough matter to curve the universe and close it. In a closed universe, literally, if you look far enough in that direction, you'll see the back of your head, okay? And so the idea was to try and determine how much matter there was, measure the expansion rate, and determine if the universe were open, closed, or flat, and then we would know whether our universe ended in a bang or a whimper, okay? Now, we have been able to do that, and those are the things I want to talk about in the next few minutes. We've been weighing the universe to determine how much matter there is. We now know how fast the universe is expanding, how much matter is there. How do you weigh the universe? You stand on the shoulders of giants. This is an old guy named Tycho Brahe, whose work eventually allowed Newton to develop his theory of gravity and eventually allowed us to weigh the Earth and the sun and our own galaxy. But nowadays, in fact, we use gravity to weigh the universe in a slightly different way. And I just want to show you a picture, which is worth 1,000 words in this case. This is the way we can actually, and this has only been possible in the last decade or so, determine how much matter there is in the universe by weighing the largest objects in the universe. This is what most galaxies hang out in clusters. This is a picture, one of many Hubble-like pictures, which are really amazing. Every point in that picture is not a star, but a galaxy. And every galaxy contains roughly 100 billion stars. So every one of these has billions of stars in it, maybe with civilizations around them, long ago gone, because these objects are billions of light years away. Many of the stars no longer exist. But the interesting thing about this cluster of galaxies, these clusters are the largest bound objects in the universe. If we can weigh them, we can weigh anything. And this picture allows us to weigh this cluster. Because, you don't have to be a rocket scientist to see there's something weird about this picture. There are all these blue things. And this is an image of something that Einstein first predicted in 1937, but said we'd never observe because he underestimated observers, which is easy to do. It's a phenomenon called gravitational lensing. Einstein told us that mass curves space. And if I have a big enough mass, and I have an object behind that big enough mass emitting light, the light will bend around it. And that light can be magnified, just as the light going through my glasses is magnified so I can see all of you. Or if I had a very irregular surface, like a crystal goblet, if I looked in it, I'd see many different images of all of you. And that's exactly what's happening here. We now know that each of these images, these blue things, are different images of a single galaxy located billions of light years behind this cluster. And the light from that galaxy has been magnified and distorted, so we see many different copies of the galaxy due to gravity. Now, it's a beautiful phenomenon, but it allows us to weigh the cluster because we know how general relativity works, and we can ask how much mass is in this system and where is it distributed so that we can see this image. And here is the inversion of this image to determine where the mass is in this system. Where each of the little bumps is where a galaxy is. But what you see, first of all, very importantly, is that most of the mass, by far the majority of the mass in this system, is not where the galaxies are. It's between the galaxies. It's stuff that doesn't shine. And we now know that almost 30 times as much stuff in the universe is out there and is dark as compared to all the stars and all the galaxies and everything we can see. 30 times as much stuff. And physicists, with their great linguistic perspicacity, have called this stuff dark matter. Okay? And one of the big mysteries is, what is this dark matter? And one of the things that makes it really exciting is that we realize there's too much dark matter to be made up of normal stuff. I don't have time to explain the arguments, but we know for very good reasons to believe that that dark matter is not made of protons and neutrons and the same stuff that you and I are made of. We think it's made of some new type of elementary particle created in the earliest moments of the Big Bang. A type of elementary particle that doesn't interact with matter like normal matter does. And what makes that interesting is that we don't just need telescopes there to find it. If it's uniformly distributed in galaxies, like our own galaxy, it's in this room. It's going right through your bodies as you doze off during this lecture. Okay? And that means we can build detectors to look for it. In fact, there are detectors underground around the world, like this one, which has a block of germanium cooled to very close to absolute zero. And most dark matter particles are going right through this thing without ever knowing it's there, but every now and then one may bounce off it, we hope, depositing a little bit of energy, heating the whole thing up so we can measure it. And then we could try and determine maybe what this stuff is made of. But to go back to that other picture, what we've been able to know, in fact, physicists, whenever they have an important number, give it a Greek letter. And so we call this thing omega. And what we've been able to measure is omega is 0.3. What does that mean? Omega tells us how much matter there is in the universe compared to how much matter we need to have to make the universe just close on itself. If omega is 1, the universe is flat. If omega is bigger than 1, the universe is closed. And if it's less than 1, it's open. So we seem to have discovered with great accuracy that we live in an open universe. That big holy grail of cosmology looks like it's been finally solved. We live in an open universe. But there's a problem. First of all, a theoretical problem. Theorists knew that the universe couldn't be open. Omega has to be 1. We knew that. Why? Because omega equal 1 is the only pretty number. And so we figured it had to be 1. And there's a big problem because none of the observations told us it was 1. And so there's a big problem as we finally got this number down pat, it caused a big puzzle. But now there's another way. It turns out we can measure the geometry of the universe. Instead of adding up matter and comparing it to the expansion rate of the universe, we can actually measure the geometry of the universe directly. And we can do it using one of the strongest tools in cosmology that we'll talk about. In fact, Lyman Page is here as one of the people directing one of the programs to look for this stuff. So the question is, how would you measure the geometry of the universe? Well, the question you could ask is, how would you measure that the Earth is curved if you couldn't go around it, you couldn't sit in a satellite and see it? Well, very simple. You draw a triangle, and then you ask a European high school student, what's the sum of the angles in a triangle? And then they tell you it's 180 degrees, okay? And you say, okay, you learned your geometry from Euclid. But in fact, on a curved surface, like the surface of the Earth, I can draw a triangle that's very different. If I take a triangle where I go along the equator, make a right angle, go to the North Pole, make another right angle, come back to the equator, I now have a triangle with 3 right angles. And 3 right angles adds up to 270 degrees. So if I could draw a big enough triangle on the surface of the Earth and see that it differed from 180 degrees, I'd know that the Earth is curved. It turns out that that thinking works exactly the same for a curved 3-dimensional universe. If we could draw a big enough triangle and measure the angles, we'd know whether we lived in an open, closed, or flat universe. And that's what we've been able to do in the last 10 years or so. We've done it using this great observable in cosmology that's really turned cosmology into a precision empirical science. It's called the cosmic microwave background radiation, the afterglow of the Big Bang. It was discovered by accident in New Jersey, of all places, about 40 years ago by two people who really didn't know what they were doing, but we won't go into that. It's the afterglow of the Big Bang. And what is it? Well, when we look out at galaxies that are, say, 1 billion light years away, we're doing cosmic archaeology because we're looking at them as they looked 1 billion years ago. Now, given that, you'd think if the universe is 14 billion years old or so, if you looked out 14 billion light years, shouldn't I see the Big Bang? The answer is yes, if you could, but you can't. And the reason you can't is, well, the same reason I can't look outside this room. The wall is opaque. I can't see past the wall. And if I look out the universe, at earlier and earlier times, the universe was hotter and hotter and hotter. And at a certain time, the universe was so hot, when it was 100,000 years old, it was so hot that the universe was 3,000 degrees. And at that temperature, it was hot enough so that hydrogen, which is the dominant stuff in the universe, gets broken apart into protons and electrons, charged particles, and it becomes what's called a plasma. And a plasma is opaque to radiation. So we can't see past this point because the universe is opaque here. Now let's run the film forward. The universe is cooling down, and it gets to a point when it cools down to 3,000 degrees Kelvin. Protons can capture electrons, become neutral. The universe becomes transparent. And just like this room, I can see all the way back to the point where the universe was opaque. And what I would expect if there was a Big Bang was to see radiation coming at me from all directions at the point when the universe first became transparent. And that radiation was 3,000 degrees in temperature then, but it's been cooling down, and we would expect it to be about 3 degrees, and that's the cosmic microwave background radiation that's been discovered. And what makes it so neat is if we look at that radiation, we get a picture of what the universe looked like when it was only 100,000 years old. And that picture is so profoundly interesting, it's already 2 Nobel Prizes have been given for it. But for our purposes, there's one distance scale that matters on that picture, and that's 1 degree across. Why 1 degree? Well, that's about 100,000 light years across. Now, Einstein tells us that no signal can move faster than the speed of light. And that means if this is 100,000 light years, at the time, it's getting so scared that it's shaking, that at the time the universe was 100,000 years old, guys back there, stop drinking. Okay. Then no information could travel from here to here. That's, if I send out a light beam, it can only travel that far at that surface. That means nothing that happens here can affect anything that happens over there. And that's interesting because let's say I have a lump of matter that's that big. Well, it knows it's a lump. It'll start to collapse, and then it'll heat up, and pressure will respond, and all sorts of interesting things will happen. But if I have a lump that's this big, it doesn't know to collapse. It's like Wile E. Coyote when he goes over the cliff, okay? It doesn't know it, because light can't travel across it, and gravity can't even travel across it. So it doesn't know it should collapse. So the largest objects that will have significantly begun to collapse at that point are 1 degree across or so. That's the ruler. Because if we look out at this known distance, we have a ruler that's 100,000 light years across, and we look at it and we say, well, if the universe is flat, light rays travel in straight lines. And that means the angle I would expect to see by a ruler 100,000 light years across at that point would be 1 degree. But if the universe is open, then light rays diverge as we go back in time, and I expect to see the ruler would look smaller. It would only subtend, say, 0.5 degree on my eye. If the universe is closed, the ruler will look bigger because light rays converge. So all I have to do is look at that image and say, what size are these lumps? Are they 0.5 degree, 1 degree, 2 degrees across? And that's the type of thing that we've just begun to be able to do in the last decade. One of the first experiments to be able to do it was on the Earth, in fact, in Antarctica. This is a microwave radiometer, this is a balloon, and this thing was sent way above the Earth because it's looking for a background that's 3 degrees, and the Earth is much hotter than that, so you want to get above the atmosphere. And this balloon went around the world, which is easy to do in Antarctica. And in fact, right here, it's really easy to do. But here it took about 2 weeks to go around, came back to where it began, which is why this experiment was called the boomerang experiment. And it took an image of the microwave background radiation. And here's one version of this image. where the original picture is put on top. But this is just to demonstrate our cosmic myopia. Because, you know, we've evolved, and I'm allowed to say that because I'm not in Ohio, we've evolved so that our eyes detect visible radiation, and if, however, we had evolved to detect microwave radiation, day or night, we'd look out and we'd see that microwave background radiation. And these hot spots and cold spots in that radiation are the lumps. And the question is, how big are they? Well, this is a different false color image of this. These are images of a universe created on a computer. If we live in a closed universe, the average lump should be this big. If we live in an open universe, the average lump should be about that big. Well, this is bigger than these lumps. This is smaller than these lumps. But just like Goldilocks, if we live in a flat universe, it's just right. And I think I hope, yes, a much better image taken with the WMAP satellite, which Lyman Page will talk about, which shows us we can do the same thing over the whole sky. And it turns out we can do a much better, much more accurate analysis, and we find out to great precision that the universe is flat. Now there's a problem, if you've been awake. We proved the universe was open. There wasn't enough matter to make the universe flat. We've now proved the universe is flat. Where's all that extra energy? We only have 30% of the amount of stuff to make a flat universe, but we live in a flat universe. Where could that extra stuff be? Well, it could be right in empty space. This is a picture of what empty space really looks like. It's not so empty. Due to laws of quantum mechanics and relativity, empty space is a boiling, bubbling brew of virtual particles that pop in and out of existence in a time so short you can't even measure them in general. And you might say, well, that's like counting angels on the head of a pin or something. You can't see their effects directly, but their indirect effects are profoundly important. In fact, this is a picture of what space inside of a proton looks like. These particles are popping in and out of existence, and they're actually responsible for most of the mass of a proton. Most of the mass of your body is not due to the quarks that are sitting in the protons, but due to these fields that are popping in and out of existence. So they're vitally important. Now, if empty space has stuff in it like this, popping in and out of existence, and it can give mass to the proton, maybe empty space can have energy. And we can ask, the same kind of physics that tells us this, how much energy does it give to empty space? We do the calculation. We come up with the worst prediction in all of physics. We predict about a gazillion times as much energy in empty space as there is in all matter in the universe. And that is pretty worrisome. Now, a long time ago, when I was a graduate student, this problem has been around for a long time. We solved it very simply in our minds. We said, a miracle occurs, and somehow we get rid of all that, and the energy of empty space is zero. That seemed about the only sensible way of solving the problem. But physics is an empirical science. And what if empty space has energy? Well, general relativity tells us that if you put energy in empty space, it's not gravitationally attractive like everything else. It's gravitationally repulsive. It produces a repulsion. And what would that do? If I put energy in empty space here in the universe, what would it do? Well, the universe, as it was expanding, instead of slowing down, would speed up. And about 8 years ago, people used those supernovae to try and measure the velocity of supernovae as a function of distance away from us. And in a sensible universe, that we should measure something that looks like that as the universe slows down. If it was accelerating, if it was dominated by the energy of empty space, it should look like this. In 1998, two different groups found a remarkable result. This may not look that remarkable, but in fact, here's this Hubble curve I showed you earlier. And if I just, for fun, draw a straight line through this and try and make it horizontal here, if the universe was slowing down, these distant supernovae would fall along this curve. And they don't. They're above the straight line. And what does that tell us? It tells us that the expansion of the universe is speeding up. And just for fun, if we try and fit that curve, what do we get? We get 70% of the amount of energy needed to make the universe flat must exist in empty space. That's exactly what we were missing. So everything holds together with this cockamamie universe that we don't understand at all. The universe is dominated by the energy of empty space. We don't understand why it's there. We don't have the slightest understanding why it's there, and if anyone comes out and tells you they do, especially if they're a string theorist, you shouldn't believe them. Sorry, Brian, wherever you are. But But we think, one of the things that makes it what's so exciting about it is we don't understand it, but we think it's related to the physics of maybe the beginning of time, which is what we're going to talk about in the panel, among other things. And so measuring it and trying to understand it may give us important information about how the universe began, and it will ultimately determine our future. And I wanted to have a New York poet here, so I quote Yogi Berra, who said, "The future ain't what it used to be." And it turns out our picture of the future of the universe is vastly different, and maybe we'll talk about it, maybe we won't. But I just want to point out that that's where we're at. We live in this cockamamie universe. If you take away everything we see, the universe would be largely the same. We are completely insignificant. Everything we see, all the stars and galaxies, planets, aliens, everything, take away them, we are just a 1% bit of pollution in a universe that's dominated by dark matter and dark energy. And we don't know the makeup of dark matter, and we don't have the slightest understanding of dark energy. So it's incredibly exciting if you're a theorist, and incredibly challenging if you're an experimentalist. And I don't know what the future is going to bring, but I do know that every time we open up a new window on the universe, it surprises us. And we have a lot of new windows that are going to open up. On the large scale, we have Next Generation Space Telescope and other proposed experiments that are going to try and probe dark energy. On the smallest scales, in fact, this year, a new huge particle accelerator is turning on, in fact, this very month, in Geneva, Switzerland, because we don't have enough money in this country to spend for these things. And it is going to turn on and produce the highest energy collisions that have ever been observed on Earth, trying to recreate the earliest moments of the Big Bang with incredible detectors built underground, the Gothic cathedrals of the 21st century. And the information about the beginning of the universe may come from the Webb Space Telescope. It may come from the Large Hadron Collider with that Ouroboros, understanding the universe on the largest and smallest scales. So to end this little introduction, I want to just say two things. Okay, first, you are completely insignificant. And secondly, it turns out the future is miserable. But you should not be depressed, because with our telescopes and our accelerators, we have been, as you can see in the last years, changing our picture of the universe more than we could have imagined beforehand. And so instead of worrying about the future and our insignificance in it, we should really revel in the fact that we, living in the middle of nowhere, in a remote corner of the universe, have an intelligence, an endowed intelligence that we can use to understand the universe. And so instead of being depressed, we should enjoy our brief moment in the sun. Thank you.
Have a seat, have a seat, have a seat. You know, yesterday Lawrence didn't know a thing, but he did stay at a Comfort Inn last night, I think, and he sort of learned all that overnight. I want to invite our panelists, come on up, invite our panelists to come and take chairs. We have, for the next 45 minutes, we're going to pick up where Lawrence left off and talk about those first few instances at the beginning. What happened at the beginning? How do we know what happened at the beginning? What is the beginning all about? Was there something before the beginning? You know, and we have a distinguished panel of experts who are going to talk to us about it. Let me introduce them. Sitting right next to me is Lyman Page. He studies the earliest universe by measuring the imprint left on the cosmos by the Big Bang. Lawrence talked about the microwave background radiation. Lyman Page studies that. He is a physicist, the Henry DeWolf Smith Professor of Physics at Princeton University. Welcome to the panel.
Thank you. Great to be here.
Now, what is the significance of all of this, and where does it fit in history and cultures trying to discuss where we came from and where we're heading? And that's why we invited Helge Kragh. He is one of the world's leading historians of cosmology. He's the author of several books about the history of physics, and he comes all the way from Denmark, from the department, History of Science department at the University of Aarhus in Denmark. Welcome, Helge Kragh. Now, Lawrence talked about the Big Bang theory and how everything started from the Big Bang, but that may not be the only idea about how the universe started. So Paul Steinhardt is here to talk about those first few microseconds and possibly other competing theories. He is a theoretical physicist. He is one of the architects of this inflationary model, which says that the universe began as this rapid accelerated expansion shortly after the Big Bang, and he is the Albert Einstein Professor of Science and Professor of Theoretical Physics at Princeton University. Welcome to the panel, Paul.
Thanks, Alex.
And of course, Lawrence will be here to kibitz whenever he can about what we're talking about. Hopefully, he'll stick around. I'm sure he will have some great information to add. But I want to ask you, Paul Steinhardt, about universes, about one of the problems, the biggest problem that they were outlining at the end of their talk was, how does something come out of nothing? How do we have a universe that comes out of nothing? Or did it not come out of nothing?
Well, that's a fundamental question which challenges everything we know about physics, because we know of no phenomenon in nature where, say, things come in and then nothing comes out, or you begin with nothing and then something occurs. So we know of no phenomenon in nature which has this property that we observe in our everyday world. So so theorists are really speculating that somehow something is special about the Big Bang that's different than any other phenomenon that we've seen when they have this idea of a beginning. Mm-hmm. For this very reason, there are some of us that think that maybe that's the wrong idea. The Big Bang is not the beginning, that there's something that comes before, and that we can actually trace things back.
Such as?
Well, one of the ideas that some of us have been thinking about is that, in fact, there was a universe evolving before the Bang, a universe that went through the same sort of history as we've observed since the Bang. It continued this way, evolving for a period, say 1 trillion years. Then a sequence of events occurred where, after it had sort of emptied out of all the matter and radiation that it had expanded enough that the matter and radiation was almost perfectly dilute due to the acceleration effect that Lawrence mentioned. Suddenly, gravitational energy is transformed into new matter and radiation, which begins a new period of evolution. And this could repeat itself in a cyclical way. So maybe the Big Bang is not the beginning. Maybe it's a transformational event, and that the evolution of the universe is cyclical.
So it goes over and over and over again.
That's right.
So of course, people are going to say, what happened before that?
That's right.
Before the cycling began.
Well,
you can't get away with that answer. We're too long with this crowd. I can see that.
That's right. Well, I mean, there's two logical possibilities. There was some beginning, but it wasn't the Big Bang. It was some event that occurred many cycles ago. Or one of the interesting ideas is that it could have been cycles forever, like
our concept
infinitely
of
number
time
of cycles.
Our concept is time is wrong.
That's right. That's right. So that we have to change our views of things, and this leads to two different pictures of where everything in the universe came from, where all the structure we see in the universe came from, that we can actually distinguish experimentally.
Helge's busted here. Let me say something.
Yeah. Yes, I want to emphasize that we need to be very cautious with the terms that we use, and that there is a whole lot of difference about speaking of the origin of the universe, that the universe has existed for a limited span of time, and then to speak about a universe which came into being, or even worse, a created universe. Because these words are not the same. Sometimes I like to phrase this philosophical insight, which is quite trivial, really, by saying that we know that the universe has an age of approximately 13 billion years, and yet it has always existed. This is a true statement. There's no contradiction between these two parts of the sentence.
Tell me why.
Because the term always refers necessarily to time. It's a temporal concept. And to say that the universe has always existed merely says that we cannot have a concept of time without a universe.
So time began at the beginning of the universe?
Yes. I mean, whatever model or view we have of the universe, because the universe is everything physical, including time and space, then the claim that the universe has always existed is true a priori.
I want to Lawrence, for the moment, the defender of the Big Bang, and say two things in response to what's said. First of all, as as unusual it is to imagine a universe beginning from nothing, in fact, it's not so crazy, because one of the reasons a flat universe is so pretty for theorists is if you add up the total energy of a flat universe, it adds up to 0. And that's one of the many reasons why all of us, Paul even a decade ago probably, would have argued that the universe was flat. Because if you're going to imagine a universe that began with nothing, a good value for the total energy is 0. Now, how can the energy add up to 0? Well, it turns out gravitational energy can be both positive and negative. And a flat universe is one in which the energy balances. The positive energy of motion is balanced by the negative gravitational attraction, and the two add up to 0. And so it is possible to imagine a universe that began from nothing. And then, with regard to the time question, that's not only a philosophical question, it's actually a physics question. And it could be, from a physics sense, that time literally began at the Big Bang, because general relativity, at least, tells us that space and time are related to matter, and as they get very, very dense, we know the laws of physics as we now understand them break down. And it could be that time itself wasn't a relevant quantity at the beginning, so the answer to what happened before the Big Bang is it's not a good question.
Not for you, but for me as a panel moderator, I think it's a great question. Yes, Paul.
So just to clarify, when I was talking about the cyclical idea, I wasn't arguing that it's logically impossible that the Big Bang was the beginning. It just may be physically incorrect. It may actually be that the structure of the universe as we see today was not created by events that occurred after the Bang, but it was actually created by events that occurred before the Bang, and we can actually see the evidence of that through the kinds of measurements that Lyman and his colleagues are attempting to make. And then we would be able to answer the question whether it was one story or the other story, whether the Big Bang was the beginning of time or not.
Lyman, let me ask you, you want to pick up on that, or you want to bring your props in here?
Right. We'll get to them in a second. Yeah, so the amazing thing that's happened in cosmology in the last, say, 20 years is that you can have these discussions that you've heard about and these notions from Lawrence, and they're based in measurement. That's the whole new thing. And they're based, and so Lawrence showed you a couple of pictures, and what I'd like to do is just take a step back, give you a sense for them, and give you some idea of how we can be so confident of what we're talking about, and that we can, and how these questions are posed. So if you can put up this first picture of the Hubble Deep Field. The Hubble? Ah, wonderful. Okay, so let me stand over here so I can point. So Lawrence showed a piece of this, and what I just wanted to give you a sense for was what we study in cosmology and the sizes. You heard a few numbers. Right, you know the moon, right? You can drive a good car to the moon. It's only 250,000 miles away, or about a light second, right? And the sun is about 8 light minutes. Okay, so in each one of these guys here that you can see are 100 billion suns. Okay, so that's a large number, right? So one way to remember it is Bill Gates has $1 for every star in our galaxy, in the Milky Way. Okay, and now this is a big picture, right? And that's all light. That picture is 1/50th the size of the full moon. Okay, so it takes 50 of those to make the full moon. Now, if you then go and count up all the galaxies, if you did this over all the sky, was the other number that Lawrence told you, is about 400 billion. So maybe that was the height of the internet era. So it's the same number, right, of galaxies in the observable universe. Okay, so that's the first thing. And remember, those are just pictures. These are little agglomerations of mass. Each one a galaxy. Each one 100 billion suns. Okay, so now if you can put up the egg, and I want to good. So this is the picture. The last picture, the Hubble, was relatively recently. You look back, billions of years. This is if you look back 13.7 billion years, right? And the first picture was in light that you see, like this, just like the lights in this room, just like what you see looking through binoculars. This picture, since it's the universe, you trace it back through what Lawrence told you, since it was so much younger and so much more compact, and older, These, let's forget the compact for a minute, we'll get back to that. These, since it's so much older, the light from here is not at optical wavelengths, but it's at millimeter wavelengths. So here's a way to think about this. And this is the stuff. So this is an image of the sky. Let me show you.
What would we know today that's in millimeter wavelengths? Is it X-rays?
A typical TV station is at centimeter wavelengths, a few centimeters. Like some of the TV stations broadcast elements of it at centimeter wavelengths. So here's the picture I want you to get from that. What is that? That's if we take the whole sky and we plaster it flat on a screen. So this is what you should be thinking of. So this is a beach ball of the whole universe. That light, as Lawrence told you, is from the edge of the universe. Okay? So so this is the picture. Those 1 degree spots he was talking about are all the blue and red spots on here. These are tiny variations in the intensity of power from when this radiation was emitted. So just a few 100,000 years after the Big Bang. So the picture then to have is that this is looking back to the edge of the observable universe. All those galaxies took place, and you see them inside this beach ball.
What's on the outside of the beach ball?
Okay, so great. So the outside of the beach ball is more beach ball. Okay? So the universe, let me pass these. I have a couple of these. I can pass these around.
We're going to do the waves soon.
Let's look at this. So the picture here, and these guys can, let me just pass this back. Okay. The universe now is, we're thinking about, is infinite. Okay? And it always has been infinite. So that's why I want to get back to the compact, right? The part we see, that beach ball, inside that beach ball, was more compact, down to the grapefruit size early on. But what happens is this radiation, since it's the speed of light, it travels the age of the universe till it reaches us, sort of carves out a piece of the universe that's accessible. And that's what we call the observable universe. So when we think of space, we think of it as being infinite, and we just access a small chunk of it.
Thank you. That's
okay?
Great explanation.
Is that?
Yeah, thank you.
Good.
Helge, let me ask you, this is a question that's been asked by the Greek philosophers. Basically, we're talking about the same question, where did we all come from, right? Where are we headed? Because that's what this ball is going to talk about.
Yes, that's relating, of course, to man's place in the universe, or the role of humanity compared to the universe as such, and that was a very important part in early cosmology, but as we heard, in very directly expressed, we are totally insignificant. And I'd like to add just two small things, that this sort of insight or recognition that not only humanity but also the Earth is an insignificant place in the universe is sometimes known as the Copernican principles, because in a certain sense it goes back to the 16th century. And for a very long time it has been a paradigm in scientific cosmology that the Earth is no privileged place, that the time that we live in is not privileged, and that human observers are not privileged. But as you may know, some of you may know, for a couple of decades, a new controversial point of view or principle named the Anthropic Principle has created a lot of discussion in cosmology and physics and elsewhere. And this principle, although it exists in many different versions, tell us essentially that human observers are not insignificant. They are all important. The name anthropic is, after all, derived from the Greek name of humans. And, well, there are different points of view with regard to the Anthropic Principle, but some people, including Martin Rees, take it very seriously. Other people will say that it's not true science, it has no explanatory power, and it's worrying return to philosophical and even theological
Let me
thinking.
explore that again a little bit. Are you saying that the fact that anything is here, the Anthropic Principle, the reason anything is here is because we are here to observe it and make it happen?
Yes, indeed. According to the so-called strong version of the Anthropic Principle, the existence, well, not necessarily of humans, but the existence of beings being made up of carbon atoms in some advanced combinations can be said to be the reason for the existence of the entire universe.
Lawrence?
And that, of course...
It's kind of simpler if you think of the possibility of many universes, which many of...
I want to get into that, too.
Yeah, and it's currently in physics, we think it's quite likely there are many universes. And then you could imagine, and so it's a little less mysterious if you put it that way, because then you can say, well, in each universe, say, the laws of physics could be a little bit different, or the initial conditions could be a little bit different. And it turns out, of course, unless things were just right so you could have galaxies, if you didn't have galaxies, you couldn't have stars, and if you didn't have stars, you wouldn't have planets, if you didn't have planets, you wouldn't have astronomers. And so the fact that we're here just validates that the laws of physics have to be able to produce astronomers. It's like an intelligent fish asking, why is the universe made of water? If it wasn't, the fish wouldn't be there to ask the question. So it's a little less mysterious if you put it that way. And so the question is there any fundamental reason why the laws of physics are as they are? Or could they be anything and they just are as they are because if they were any different, we wouldn't be here to measure it? And that's the current debate that's happening in physics, largely because of this energy of empty space, which is so weird that it's caused some physicists to go crazy.
Right. But
Actually,
I'll move down the aisle. Paul, you want to-
actually, it's more than that. I mean, it really ties together this whole story.
Yeah.
That beach ball that Lyman is showing has in his lap there, that pattern has two possible explanations. One that arises is that if the universe has a beginning, if that happened 13.7 billion years ago was the beginning, then the only way we know how to make that pattern and make the flatness and the smoothness of the universe we see is to have a period of inflation. And the original idea is that what inflation did is it took an initially chaotic universe and made it everywhere the same.
And inflation, for people who don't understand inflation, that was some rapid...
It's a period like the present-day acceleration, but at a much more rapid rate, that it would have occurred shortly after this beginning and would have taken some random distribution of energy, smoothed it out, and then this inflationary energy would have decayed into the matter we see, and that's how we got to be the way we are. And it would have left, because this decay of energy occurs through a random quantum process, it wouldn't have occurred everywhere exactly at the same time. It would have left some regions hotter or cooler than the others, producing a pattern which agrees beautifully with the measurements in that beach ball. That is one possible explanation. But along with that, but there's a surprise, a sort of kicker with that idea, which is that it doesn't do quite what we thought. It doesn't make everywhere the universe the same. Once inflation starts, it never really stops. There are always, due to rare quantum fluctuations, some pieces of the universe that continue to inflate. So in fact, what really happens with inflation is that it inflates a large piece of the universe. Part of it decays into matter and radiation, leaving a pocket of stuff, okay, whilst the rest of it continues to inflate. Then another decay process occurs, another pocket universe occurs, which contains stuff, another one, and so you get this multiverse picture. And one of the problems or issues is these different pockets have different physical properties. So for example, we point to this map and we say the universe is flat. Inflation flattens the universe. But actually, there's an infinite number of these pockets in which the universe is not flat, and an infinite number which are. So we end up with this idea there's different possibilities for the universe, for its flatness or not flatness, or for its physical laws.
So you
and
could,
inflation leads to that.
have your cake and eat it then. You could have
Well,
just
it's not
about
clear.
anything that
Well,
has to
I view it as
Yeah.
a problem. I view it as, I call this the unpredictability problem because it means that you thought you had a theory that explained the universe, but actually it produced many different universes other than the one that you see, in addition to the one that you see.
So instead of simplifying it, actually made it more complex.
Well, it may, in fact, the
It
big
lost
problem
its
is
predictive power.
it may change the nature of science because you got to ask, instead of a theory of everything, it's a theory of anything.
Right.
And a theory of anything, is it science? I mean, if you could explain anything you could see, then you could never falsify it. And that's a big worry. It's a big worry in modern physics.
Yeah, I just want to follow up on Helge and Lawrence's comments. I mean, the reason you can talk about these wild things and anyone will listen, other scientists, is you can make measurements, right? And the thing is, multiverses, no one knows how to make a measurement that can say whether that is true or not. The only way to get at that is to follow it through and make some prediction which has an effect on the universe that we see. The Anthropic Principle, same thing. There are no predictions. And so for making headway, and this is a philosophically you can see we're very different. For making headway, you have to make models that make predictions. And again, the key thing with this, with this measure, since we can measure the sky so well now, measure this cosmic microwave background radiation, we can measure it so well. We're on the verge of making measurements of detailed predictions of, say, the inflationary model of the universe. It says the sky has to act just like this. And we, in fact, are seeing that. Another way, this is taking Lawrence's picture. When we look at these hot and cold spots, these are pictures of the quantum mechanics of the early universe, writ now large across the sky. And by looking at them in detail, we can start to sort out these various theories. And it's stunning. That's what keeps us all up at night doing this. It's really exciting, and it's happening.
So is there any way to actually settle which picture is correct? You said now we can test out some of these theories.
Yeah, I would like to say that, that the alternative I was mentioning, the cyclical idea, does not lead to this multi-universe picture. So really what's at stake is not just a question of is it inflation or a cyclic model, or a question of whether there was something before the Big Bang. But are we going to be forced to this idea of multiverse, and we can only understand a small section of the universe and anything was possible, this kind of science or pseudoscience, or are we going to be led to an idea of a unified universe? And so that's also at stake.
Why do we believe this? You brought up the multiverse. Why should we think there is such a thing?
Well, Paul already mentioned that the best ideas we have, or at least one of the best ideas we have of the early universe, naturally predicts many other universes. It predicts that phenomena, in fact, it's kind of philosophically almost like returning to the steady state universe. On the largest scales, if this picture is true, on the largest scales, at any instant, there's always some universe being born, and another one may be dying.
But wouldn't we feel the effects of another universe?
No, we wouldn't. And
could we be in the middle of one? Or
no, and so the question is this philosophy? And I want to get back to Lyman's point. Yeah. It isn't. It's actually physics, because for the following reason. Let's say we actually had a theory, which we don't have, but let's say we had a theory that actually predicted the mass of the proton, the mass of the electron, why there are 3 generations of elementary particles, why there are 4 forces in nature, all of these things. But it also predicted that there had to be this phase of inflation in the early universe. Well, it would make 100 predictions that we could measure and test, and one that we couldn't, that there were other universes. And so we pretty well believe that those other universes are out there. It could also, but the key point is that that these models also, and one of the things that sort of the theory that Paul's promoting versus inflation, some of these things do predict measurable differences in that pattern of dots. And so we're not guaranteed by any means that we're going to be able to settle this. But there's great excitement about the possibility that by measuring that pattern of dots, or even looking for something even more interesting, it's called gravitational waves from the early universe, we may be able to distinguish these pictures. We don't know what the future is going to bring, which is why it's interesting.
Stay tuned.
Yeah, but we need to keep looking.
Question here. Yes, sir.
Hi. Just first a quick clarification question for Lyman in terms of, could you, as the beach balls are running around the audience here, could you explain the apparent discrepancy between the beach ball and the picture in terms of for example, the large red stripe and things like that? So that's my first question.
It's a sharp audience.
Yeah. Okay, sure. So yikes. Oh. Universe on the loose. Here we go.
It's a parallel.
Yeah. Yes, that one. So we're in the galaxy, right? And we have to look out through the galaxy. That picture that we splash around has the galaxy subtracted. This one, because we're right in the middle, right, looking out, we have to look out through the galaxy. So this red ring around here is us looking out through the galaxy.
Our galaxy.
Our galaxy, the Milky Way.
Okay.
Right.
Second, for the panel, in terms of the kind of many universes theory that's recently kind of cropped up, could you relate that or not relate that to when people first realized that superposition existed, and one sense was, well, let's different states collapse, superposition collapses to one state or the other. Obviously, Everett and others said, no, maybe they don't collapse. Maybe two universes, so when we observe something, and it looks like this beam was split, and it went this way and that way, and then it collapsed one way or the other. No, Everett said, no, two universes were created upon that observation. That the observation itself created now two strands, two streams. Can you relate the two, or do you find them completely different? And finally,
wait, does anybody know what he's talking about? Maybe a few people. Lawrence will straighten it out.
Yeah, okay. So unfortunately, there's many different ways of talking about many universes in physics, and this is actually different. The quantum mechanics is really fascinating because it says that on small scales, the universe is really crazy, and objects can do many different things at the same time. Too bad. You don't like it? Too bad. That's the way it is. And it turns out, when you actually measure it, you find out, well, no, it was doing one thing. What the picture he's talking about suggests is when you measure it, yeah, you force it to be doing one thing, but in fact, every measurement, because the object was doing many things, every measurement forces you to exist on what's called one branch of many universes, and in a different, had the quantum mechanical measurement come out a different way, you would come out with a different number, and in a different universe, I'd be asking the questions and Ira would be answering them. And it's just, there are many, many universes, and we're always measuring on it. Every time we look out, we create a new universe. It's a weird and crazy picture to try and understand quantum mechanics, but it's very different than this picture. This picture is many physical universes in the same, if you wish, the same quantum mechanical branch of the wave function.
Okay. I've got a mic here. Thank you.
You're welcome.
Is the idea of inflation necessarily that matter has moved at speeds perhaps greater than the speed of light, or that the way we measure has changed, that the ruler has changed?
You want to take that?
Well, so when we talk about inflation, it fits in this idea of expansion, like the Hubble expansion that Lawrence described, except that the rate of expansion is increasing with time. So, for example, imagine a situation where the universe doubles in size every 10 billion years. That's roughly speaking what seems to be happening in the universe right now. So space stretches by a factor of 2 in every direction every 10 billion years. So something which, a distant galaxy which is now, say, 1 million light years from now, will in 10 billion light years be twice that, then another 10 billion light years, twice that again, so it's gone twice as far in the next 10 billion years as in the first, and then another 10 billion years, it goes yet twice as far as that. So it's separation from us, it's picking up with time. If you could imagine that situation, if it continues over time, it eventually dilutes or spreads out all the matter in the universe to the point where the universe becomes essentially empty. This is what's happening in the universe in the future at a rate of doubling of about every 10 billion years. Now, the idea of inflation is that there was another thing, just like dark energy. It was short-lived. It eventually decayed into matter and radiation. But before that happened, it was also causing the universe to double in size, but not once every 10 billion years, once every 10 to the minus 35th seconds. Okay, so in just an instant of time, 10 to the minus 30 seconds, so one with, a decimal point and, let's say 30 zeros and a 1 or something like that. In that instant of time, it could have doubled as much as 100,000 times. Well, if you take something the size of a proton, you double the region the size of a proton, you double it 100,000 times, you get to a region which is much greater than anything we've been able to see in the universe up to this point.
Do we know why that suddenly would decide to do that at that point? It's been described to me like opening a soda bottle. Suddenly the fizz all comes out and it settles back down again. Is that the inflation of the bubbles coming out?
Well, it's not required. So the idea that there's a beginning doesn't require inflation.
Doesn't require.
We have to add in something. Just like we have to add in something to explain dark energy, we have to suppose that in order to explain the universe we see, there had to have been, if there was a beginning, the only way we can get this smooth universe is to suppose there was such an element in the universe that, on the one hand, causes inflation, and on the other hand, decayed away.
So this is a mathematical trick.
No, but
it's a theory. It's a hypothesis.
It's not just added for cosmology. We should say that we're not just inventing things because that particle physics tells us that there were lots of things called phase transitions in the early universe. The nature of the universe changed. The forces that we now see that look very different. We know that at least 2 of the forces that we now see that look very different, the weak and electromagnetic force, were once, when the universe was about a millionth of a second old, looked very similar. We think that 3 of the 4 forces probably look very similar at a time around 10 to the minus 35 seconds. And when a phase transition happens, just like when water turns to ice, you can trap energy. And that trapped energy, if it happened in the early universe, could produce inflation. So there are kind of natural mechanisms. It's not just something we're inventing on the...
Well, we should be a little bit cautious, because to get the inflation we need, it can't just be any old phase transition. It turns out it has to be very finely tuned.
Absolutely.
And that's a big issue as to why it would be so finely tuned. So it's not going to, so there's some of the ingredients you need naturally,
Absolutely.
but they have to be just so.
I understand how you have to be careful about talking about inflation with the price of oil and stuff.
Exactly,
Like,
right.
There was a,
Let me
you want to go
just
ahead?
add one little bit to that. Right, I think the picture most of us have of the Big Bang is absolutely not one of mass being thrown out from some beginning. That's not it. I think a much easier way to think about it is, well, of course, all the mass we know today was in even protons or quarks before then. But as you can think of these galaxies as markers of space, and it is the space, the currency of inflation of all these models is space. It is space that's changing. It's space that's accelerating.
That's a hard concept to
Right,
get
and
your head
that
around.
is
It's a
the
very
concept.
hard concept to space.
And matter is at rest in space.
And matter's at right. Matter's
it's
at
really
rest.
weird, because in general relativity, you can be at rest and moving at the speed of light at the same time.
Yeah.
You're at rest locally, but some other region is moving away from you at the speed of light. It's crazy. It's just the way it is.
So
Discuss.
yeah.
Okay, question, sir.
Yes, I was going to ask a question from the visitor from Denmark. When you talked about I think you called it the Anthropic Principle, and it relates to what the first gentleman asked. The concept that sort of, that you really don't know if there's a universe behind you until you turn around, the wave function collapses and you're able to observe something. So can you expand upon what you were talking about in that principle and how that interacts with that concept?
I don't know how the Anthropic Principle relates to the quantum mechanical principles, but in a certain sense, the Anthropic Principles can be said to be merely a principle of consistency, that everything that we observe and that we know exist, they have to be consistent with our being. And if that is the case, the Anthropic Principle is not very interesting. It's almost a rather trivial observation. And as it was indicated, the standard test of whether a statement or a theory is scientific or not is that it leads to a certain kinds of predictions, and that these predictions are testable. And I think it's generally agreed that the Anthropic Principle, which has been on the scene for certainly, 40 years or something like that, has not resulted in testable predictions. And from that point of view, it's really surprising that this principle is still taken very seriously. I remember when it emerged and became an issue, I thought that it would, that's the sort of silly ideas which come up and they would probably evaporate next year. But this did not happen.
Let's
I
hope
don't
so.
know why.
Let's hope by next year.
Yeah, we hope so. But it's really the dark energy that's so inexplicable.
Right.
The only, right now, unfortunately, the only good explanation of why it's there at the value it is an anthropic one. Now, it's not very satisfying, but it's forced a lot of physicists to think that maybe that's the explanation. And again, I agree that I certainly hope it goes away. But
and if I mean,
not sure it's a good
very briefly, no.
So you'd like to take that, you'd like to find an explanation that does away with the whole Anthropic
Well,
Principle,
the whole reason for
especially
doing
with the dark energy.
the whole reason for doing science, I believe, is that you have to have predictive power. The measure of currency, or the measure of the validity or power of the value of science is its predictive power.
Because if it doesn't have that, it's just blind faith that something
You're doing
is true.
some other
If you can't
activity.
test
You're
it-
doing some other activity,
Right.
which is not science.
Science means you have to make a prediction and you have to test it, or else you just believe it on faith and
Right.
it's not science.
the neat thing about science is that most theories are wrong. I mean, if they weren't, it'd be easy. Anyone could do it.
Right.
I think it's always important to have alternatives because they help focus your attention on what tests to do to gain more confidence about which theory is right, and they also help generate new ideas for what
So you want to not just knock down the theories until you come up with the right one. You say, let's try this one, let's test it out, knock it down, let's go to the next one.
You want predictive power.
The gorilla in the room, right, is dark energy. There is no, I mean, first it was found by measurement, and there is no theory that predicts it in any fundamental way.
And talking to theorists, the problem is also, why is there so little of it, right?
Yeah.
Yes.
There should be a lot more of it. First, we don't know what it is, but there should be a whole lot more of it.
Yeah.
Right? Wasn't that correct?
There should be a lot more nothing. Yeah.
There should be a lot more nothing.
Yeah.
Yeah, and it's
You guys got your hands full, I think.
And by the way, that's the big question we were talking about earlier. Why is there anything at all? Is another, interesting. I don't know whether we want to go into it now, but that's another fascinating question we really don't yet have the answer to.
Do we know why time moves in this direction and not in another direction?
Well, sometimes it moves in that direction.
But it's a serious question. The arrow doesn't have to go in that direction.
It's a very philosophically fascinating question, and a physics question that's still, we have good ideas at some level about it, but time is a really slippery concept.
I would like to protest, and at least to
You're outnumbered.
To make clear and to argue that even in cosmology, which is an extremely ambitious science, probably the most ambitious science of all, but there are questions which cannot be answered by the cosmologist or the physicist, simply questions which are not within the realm, within the power of science to answer. It may be because they are meaningless, or it may be because they are best answered from other points of view, by philosophers, or for that matter, by theologians. And the famous or infamous question of why is there anything at all rather than nothing, which is this is a metaphysical question. Theologians have answers to that, but it is not a scientific question.
Oh no, I actually disagree there. I think one of the things that got many of us theorists into cosmology was trying to answer that question. It's amazing that I think that physics, with our understanding of what's called grand unification, suggested you could understand how a universe which basically should have ended up with nothing actually ended up with something. How matter was created out of nothing.
Yes, but
and that's a fascinating.
You are using the term nothing in a shaky and wrong sense. It's very important to say that zero energy is totally different from nothingness. Nothingness is a metaphysical concept to which no physical observable or any measurable property can be assigned by its very nature. And for this reason, it cannot be part of physics.
Yeah, okay, I'll buy that.
All right, we'll score a few points on that. I think we have time for one more question. Whoever has the mic. Go ahead, stand up. Oh, just speak up, speak up.
Oh, I have 2 questions.
Let's go one at a time.
Okay.
See how long it takes to answer these questions.
First, can you tell me the exact name of that Big Bang project in Switzerland? And also, is it a worldwide effort, or how much is NASA involved in this project?
Actually, it's not NASA. It's actually the Department of Energy, and it's called the Large Hadron Collider, the LHC. It's an accelerator, and it is a truly international effort, which is really, I think it's really important to stress that. It's amazing to me. It's an effort, each of the experiments of that Large Hadron Collider involves thousands of physicists from hundreds of countries speaking dozens of languages, designing a machine that's bigger than a Gothic cathedral. Each of those detectors has more iron than the Eiffel Tower, that have to fit together with an accuracy of microns to measure events that require so much information that each event, which happens 1 million times a second at the LHC, will generate terabytes of information. And that we're trying to analyze that. It is truly an international project, and it demonstrates to me one of the greatest aspects of science, that we can work together.
And when will the first experiments happen there?
Well, I was just there last week, and the machine is almost cooled down. The beam is being set up, and in the month of June, the beam will begin to get going, and the first collisions test collisions should begin to be by the fall.
And what do they collide?
Well, they'll begin to collide by the fall. We won't have data.
What things will they collide together in?
Protons going around 26 kilometers this direction and 26 kilometers this direction will collide at 4 different places, producing little, if you wish, little mini Big Bangs, recreating the universe as it was about a millionth of a second after the Big Bang.
There was a fear that a little black hole could be created.
Yeah, and
Remember that?
let me tell you, that's not a problem, because as energetic as those collisions are, you know, the universe, nature's a lot more powerful than we are, and more energetic cosmic rays are coming down and striking the Earth every second than are produced at the LHC, and particularly the moon. So the fact that the moon has been around for 4.5 billion years with cosmic rays bombarding us makes us pretty confident that the accelerations that are happening at the LHC.
All right, I got time for one more question, then we have to, who's got the mic close by? Raise your hand, okay.
If the universe is expanding and the mass is separating from each other at a rate of acceleration that's continuing, won't they reach the speed of light separating each other? And then what will happen?
In fact, that's one of the things I didn't get a chance to talk about, but in fact, objects in any universe, in fact, even if the universe isn't accelerating, there are always regions that are moving away far faster than the speed of light. Now, you learned in school that that's not possible, but that's because we lied. Really, you have to be like a lawyer and parse it a little more carefully. Objects can't move through space faster than the speed of light, but space can do whatever the hell it wants. And in fact, so in such a universe, and this is really fascinating, in such a universe, the longer we wait, the less we will see. Because objects that are now moving away from us less fast than the speed of light will one day be moving away from us faster than the speed of light. So in such a universe, eventually, everything that isn't bound to us now will disappear. And the universe will become cold and dark and empty. Maybe that's a good way to end.
Well, that's that's the take-home message. The universe can do whatever the hell it wants to. I want to thank all of our panelists. Lawrence Krauss, Paul Steinhardt, Helge Kragh, and Lyman Page. Thank you all for being with us. Thank you all for coming. We'll see you next time. See you on Friday.